Hi, in this video I'm going to talk about voltage-gated ion channels. So these are the channels which change the membrane potential and thus allow an action potential. So here are the channels. The white channels are the voltage-gated sodium channels and the black are voltage-gated potassium channels. Here are all the charges sitting on each side of the membrane. This membrane is currently at its resting membrane potential, which has been set up by an sodium-potassium ATPase, which is not shown here. See the previous tutorial for an explanation of how the sodium-potassium ATPase sets up this resting membrane potential. So this is the outside of the cell, or the extracellular environment, and this is the inside of the cell, or intracellular. Remember in the last tutorial we said that sodium wanted to move this way but couldn't, and potassium the other way. Well, they still can't because their channels are closed. However, if we change the voltage across the membrane by adding positive charges here and here, then this gate flips open on the sodium channel. And this allows sodium to flow into the cell down its concentration gradient. This means there is an influx of positively charged sodium ions, and the positive charges start lining up across the membrane, with the negative charges lining up on the other side. So this is a reversal of the resting membrane potential. Now remember that we also applied a positive charge to the voltage-gated potassium channel. Well, this also flips open, but there is a delay before this happens. But when it does happen, the potassium rushes out, removing positive charges from the cell and placing them on the other side of the membrane. And this returns the membrane potential back toward the resting membrane potential. These channels are both open at the moment, so they need to be closed. The sodium channels close about the same time the potassium channels open, and they close by this ball and chain method. This ball gets stuck in the channel, and sodium can't flow through anymore. After a delay, the potassium channels also close. Now, potassium can't flow, and this keeps the membrane potential back near the resting membrane potential. So if we look at a voltage recording taken inside the cell, and we look at voltage versus time, then we start with our resting membrane potential. Then we applied our stimulus, and this opened the voltage-gated sodium channels. The cells become more positive, and we can see that on this graph. Now here, the potassium channels open, and the sodium channels close. The positively charged potassium rushes out of the cell, and the cell becomes more negatively charged. And we can see that drop on this graph also. Then the potassium channels close, and the resting membrane potential returns. This up and down graph shows a typical action potential. In the next video, we will look at how action potentials propagate along a membrane such as an axon. For more free tutorials and the PDF of this tutorial, visit www.handwrittentutorials.com.